Hello all, I hope that you're doing okay with your exams. I mean, this video is recorded as you're taking the June exams, and I'm talking about A-level students in England, international A-level students, and international GCSE students. I mean, they are taking their exams this June and this May, so I hope you're doing okay. This video is about Unit 5. It's been a while since I uploaded any international A-level material, so here it goes. I found online that you're taking this exam this Friday, so I hope it comes in time, and I mean, this video comes right around the time you need it, and that it's useful. This test is from October 2024. And let's dive in. The general things I always say is that this test lasts 105 minutes. It awards 90 marks. Okay, so my recommendation is that you have to spend about a minute per mark. So if a question awards 10 marks, you should devote about 10 minutes to it. Okay. Another thing that I always forget to mention is that, guys, when you read the questions, and by the way, I'm gonna flip the page. So make sure you read all of the question thoroughly and make sure you understand what they are asking, okay? Because sometimes, as I used to tell my students, the question is half the answer, meaning that if you read and understand the question, half of the answer is already in the question, okay? So make sure you understand what they are asking. Another thing is that if you don't know the answer to a question, just skip it. Don't waste time, because not only you're going to waste your time, you will also lose your confidence and your momentum and so on. So it's preferable that you go over the problems that you know how to solve immediately, okay? And after you're done with those problems, you can always return to the problem in the end. And also, it frequently helps to just go to the back of the paper and find the formulas and the constants related to a problem, and that might give you the inspiration needed to solve the problem, okay? So yeah, I mean, these are the general things I always say. And specifically about the multiple choice section, I always say that sometimes for some questions you can arrive at the correct answer just by eliminating the wrong answers. And it's often the case that even if you cannot do that, usually 2 out of the 4 options are totally wrong. So then you're left with 2 answers to choose from, okay? So let's start with question 1. A radioactive source emits alpha radiation, beta radiation, and gamma radiation. Which of the following is correct? So A says alpha radiation is the most ionizing. Okay, I mean, that's the correct answer actually, okay? Because it is the most ionizing. So then beta radiation is the least penetrating. No. Beta radiation is the most ionizing. No. Gamma radiation is the least penetrating. Also no. I'm gonna write some notes this time in the multiple choice section. So A is the most ionizing because it has the highest mass and charge. Okay, and charge. And let me use clean space. So it has it causes the most ionization per unit length. Okay, so these are some general things you need to know about radiation. Wait, here we have to write it causes the most ionization per unit length. Okay, part B. Second question. Now, during an earthquake, steel framed buildings remove energy from the oscillation of the building. Which of the following is the reason for this? Option A, steel is a ductile material. Again, this is actually the correct answer. Steel is an elastic material. It is not. If it was elastic, it will cause large oscillations in buildings because it will give the energy back to the system. So it will be dangerous, actually. Steel is a stiff material, it is not, and steel is a strong material, it is not. So here we can write that ductile means steel is ductile. So ductile means it deforms plastically, okay? And plastically means permanently, pretty much, okay? So it deforms plastically and dissipates energy through permanent deformation, okay, rather than storing and returning the energy elastically. Okay, so this was question 2. Let's go to question 3. The graph shows how intensity of radiation varies with wavelength for two stars P and Q. Which of the following could be deduced from the graph? We cannot tell anything about the luminosity or the mass from this graph, so the answer is pretty much D. Okay, so the temperature of P is larger than the temperature of Q. Okay, to be able to tell anything about the luminosity, you also need the Hertzsprung-Russell diagram. Okay, so remember the Hertzsprung-Russell is luminosity versus temperature, but temperature increases to the left. So you have the main sequence here, the giants over there, and the white dwarfs down there. So yeah, the only thing you can tell with using this graph is the temperature. 4. A simple pendulum consists of a mass attached to a string. The pendulum is set into simple harmonic motion. The acceleration of the mass is a, and the displacement of the mass is x. Which of the following graphs shows how a varies with x? Okay, so a is minus omega squared times the displacement, right? So it's gonna be a straight line with a negative gradient and passing through the zero. So the correct answer is D. Okay, I hope this makes sense. Moving on. 5. The dashed circles on the diagram represent gravitational equipotentials about the planet Mars. The gravitational potential at X is minus 5.5 megajoules per kilogram. The gravitational potential at Y is minus 3.7 megajoules per kilogram. A meteor of mass 250 kilograms falls from Y to X. Which of the following is the change in gravitational potential energy of the meteor as it falls? So delta U, the change in gravitational potential energy, is going to be M delta V. So it's going to be M times the potential at X minus the potential at Y. Okay, so 250 times minus 5.5 plus 3.7 kilograms, and then megajoules per kilogram, which cancels. And this is minus 450 megajoules, which is option C. And another way to think about this is that the potential energy decreases as you go from Y to X. It's the same as when you are at in the gravitational potential of the Earth. If you stand on a mountain, you have more gravitational potential energy than when you are at the sea level. Okay, so if you go from the mountain to the sea level, you lose gravitational potential energy. Okay, that's why the negative sign. Okay, 6. The mass is hung on a spring. The mass is set into vertical oscillation with frequency of oscillation f. The mass of the spring is then doubled. The mass on the spring, is doubled. What is the new frequency of oscillation? So the initial frequency of oscillation is going to be 2 pi, the square root of m over k. And the new frequency, period, is going to be 2 pi, the square root of 2m over k, right? So it's going to be the square root of 2 times the old frequency. So 1 over f prime is going to be 1 over the square root of 2. Wait, I confused myself. Let me think. So t prime is 1 over f prime. Okay. So this is 1 over f, right? So f prime is f over the square root of 2. Sorry, I got confused for a moment. So B is the correct answer. Okay, I'm sorry about that. I don't know why I somehow got confused. So I hope this makes sense. If it doesn't, ask me in the comment section and I'm gonna explain it better if needed. So let's go to question 7. The universe is currently expanding, but the ultimate fate of the universe is unknown. Different conditions will result in a different ultimate fate for the universe. Which of the table correctly links a condition with the ultimate fate of the universe? So the first option, the density of the universe is equal to the critical density. And then they say that the ultimate fate is going to be that the universe eventually contracts. That's wrong, okay? Because if the density is equal to the critical density, the universe will be flat. Option B, the density of the universe is greater than the critical density, and the ultimate fate will be for the universe to eventually contract. That's correct. Okay. And then for completeness, option C, the mass of the universe is equal to the critical mass. And then the fate is that the universe expands forever. That's wrong. And then D, the mass of the universe is greater than the critical mass. Okay. And then the universe expands forever. That would be the case if the mass of the universe was less than the critical mass. So that's wrong. All right. 8. Epsilon Indi is a main sequence star. I never heard of this star before. If you know about it, let me know in the comments. And by the way, guys, about 90% of the viewers are not subscribed to the channel, which is sad. So if you, it doesn't cost anything, guys. So please subscribe if you want. So, okay, let's read the question. Which of the table gives a possible surface temperature and luminosity for epsilon Indi? So the key here is that this is a main sequence star. Okay, to think about this problem, you have to bring mentally, you have to remember the Hertzsprung-Russell diagram, the HR diagram, not the human resources, the Hertzsprung-Russell diagram. That was a lame joke, I'm sorry, guys. So, this vertical axis represents the luminosity over the luminosity of the sun, and the horizontal axis represents the temperature increasing to the left. So this is 1, and the temperature of the sun is about 6,000 Kelvin. Okay, and the main sequence stars are on this diagonal. Okay, so let's go see. If the surface temperature is 3,000 and the luminosity is 140 times the luminosity of the sun, we are somewhere here. Okay, so that's a red giant. If the surface temperature is 4,700, we are somewhere here, and the luminosity is 0.1, we are on the main sequence. So that's actually the correct answer, but let's classify the other ones. Surface temperature about 6,000, but luminosity is 1,400 times the luminosity of the sun. So we are somewhere here. So that's a red supergiant maybe, or giant, something like that. And the last option, the surface temperature is 10,000 Kelvin, so somewhere here, but the luminosity is 0.01 times the luminosity of the sun. So we are down there. That's a white dwarf. Okay, so let's move on. Okay, question 9 and 10. So questions 9 and 10 refer to the following information. The graph shows how the force F varies with time t for an object performing simple harmonic motion. 4 graphs of different quantities plotted against time for the same period of time are shown below. The scale on the x-axis is the same for each graph. Which graph shows how the displacement of the object varies with t? Recall that the force is equal to minus k times the displacement in simple harmonic motion. So x is minus 1 over k, so some constant times the force. Okay, so it's going to be the same graph as that of the force, but inverted. Okay, it's the negative, so it's option D, right? Let me think. Yes, so D is the correct answer. Okay, and then 10, which graph shows how the velocity of the object varies with t? Remember, the velocity is dx over dt, so the derivative. So if we come to option D, which is the displacement, and we take the gradient in the beginning, we see that the gradient is negative, so we start with a negative velocity, and we need a cosine function, okay, because velocity and displacement are 90 degrees out of phase with between them, right? So the only plot that works is B, okay? So B is the correct answer, okay? I hope this makes sense. Let's move on to, we are done with section A, okay? Good news. So let's move on to section B. Helium gas can be used to fill balloons. It can also be used to make you sound funny. So if you guys tried that, let me know in the comments. 13,000 years old, but I've never tried this. It's a shame, but it never happened. So I'm actually curious whether it's true or not. I mean, you kind of sound funny, so let me know in the comments. Let's read the question though. A cylinder of helium gas contains 1.2 times 10 to the 24 molecules. The temperature of the gas is 293 Kelvin. Calculate the internal energy of the helium gas. Okay, for one molecule, 1/2 m times the average squared velocity is 3/2 kT. Okay, so this is the kinetic energy pretty much of one molecule. But we have n molecules, okay? We have 1.2 times 10 to the 24 molecules. So the average energy that I will call U is going to be n, the number of molecules, times 3/2 kT, okay? So that's 1.2 times 10 to the 24, and then times the Boltzmann constant, so 1.38 times 10 to the negative 23 joules per Kelvin are the units, okay, times 3/2, and times, what are we missing? The temperature, which is 293 kelvins, so kelvins cancel, and this works out to 7,278.12 joules. So that's the internal energy. It's kind of large. I mean, I didn't expect that. So let's move on to question 12. Okay, bronze is a mixture of tin and copper. And by the way, in Cyprus we had all those eras. So we started with the Stone Age, then we had what came next? Copper age, then Bronze Age, Iron Age. You know, all these things. Let me know if the same is true in your country. But yeah, Cyprus is very old. I mean, they found settlements from people that lived here, I think 12,000 years ago. Nobody knows how they made it here because it's an island. So yeah, it's kind of a mystery a little bit. So anyway, bronze is a mixture of tin and copper. Tin melts at a much lower temperature than copper. 2.7 kilograms of solid tin at temperature 295 Kelvin is added to 10.5 kilograms of molten copper at a temperature of 1520 kelvins. The tin melts and mixes with the molten copper to form molten bronze. Calculate the final temperature of the molten bronze. And they give you the specific heat capacity of molten copper, the specific heat capacity of solid and molten tin. Is it the same? Strange. And then the specific latent heat of fusion of tin, which is 5.92 times 10 to the 4 joules per kilogram. So here the way to think about this is that the energy to melt, let's call it energy, and then this is supposed to be some sort of a subscript. So energy to melt tin plus the energy to raise T for tin should be equal to the energy to lower the temperature of copper. Okay, so I hope this makes sense. So since the tin is solid, we need to melt it first, so we need some energy that we will take out of the molten copper. Okay, and then we need energy to raise its temperature. I mean the molten tin's temperature until it matches the temperature of copper. Okay, so let's write down equations. So the mass of tin times the latent heat of tin plus the specific heat capacity of tin times the mass of tin times delta theta for tin should be equal to the mass of copper times the specific heat capacity, I don't know what's wrong with me, of copper times delta theta for copper. Okay, so 2.7 times the specific latent heat, which is 5.92 times 10 to the fourth, okay, plus 214 times 2.7 times T, which is the final temperature, minus 295. And I figured this out from the fact that the final temperature is going to be T, and we have to raise the temperature from 295 to some other temperature that we need to calculate. Okay, this will be equal to the mass of, the specific heat capacity of copper, 572, times the mass of copper, 10.5, times, it will start from some temperature of 1520 Kelvin, and it will go down to T, the final temperature, which is going to be the same for the mixture, right? Let's use a clean page. So we have 159,840 plus 577.8 T minus 170,451. That is equal to 9,129,120 minus 6,006 T. Okay, I'm sorry for the large numbers and the strange calculations, but it works out in the end, I promise. So 6,583.6 T is equal to 9,139,731. So T final temperature is 1,388.2 kelvins. Okay, I hope this makes sense. Let's move on to the next question. Okay, question 13. A student is investigating two simple pendulums. Each pendulum has the same mass. One pendulum has a length L, the other pendulum has a length L over 2. He hangs both pendulums from the same fixed support. The student displaces each pendulum, giving each pendulum the same initial amplitude as shown. He then allows each pendulum to oscillate freely. The student suggests that the maximum kinetic energy of the pendulum with a length L over 2 will be 4 times the maximum kinetic energy of the pendulum with a length L. Evaluate the student's suggestion. Okay, so the maximum velocity during an oscillatory cycle is equal to omega times the amplitude. And we know this from the fact that V is omega A sine omega t, where the maximum value for sine omega t is 1. Okay, so the maximum velocity is omega times A. So let's work this out. So V max is 2 pi over the period times the amplitude, and then we have 2 pi, and then the period is 2 pi, and then the square root of L over G times the amplitude. So 2 pi cancels. So that's actually the final result for the maximum velocity, the square root of G over L times the amplitude. Okay, so let's use that V max for the L over 2 pendulum. Okay, so V max for that pendulum is going to be G over L over 2 times A. Okay, and for the pendulum with length L, V max for L is the same expression we just derived, so G over L times A. Okay, now let's write down the maximum kinetic energy. So Ki E max for the pendulum with length L is going to be 1/2 mv max squared. So it's going to be 1/2 m G over L times the amplitude squared. For the other pendulum with length L over 2, we're going to have 1/2 m, since it's the same mass, times V max L over 2 squared. Okay, and this result is going to be 2 times, let me think, where did I get that to? Oh, I got it from the fact that V max is going to be 2 times G over L times A. So I was thinking ahead. So 2 times 1/2 m G over L A squared, which is 2 times the kinetic energy max for the pendulum with length L. Okay, so student is actually wrong. Student is wrong here. Okay, so this was question 13. Let's move on to question number 14. Microbes at the bottom of a lake release methane gas. The gas rises to the surface of the lake as bubbles. A methane bubble with a diameter of 1.5 times 10 to the negative 3 meters is released at the bottom of the lake, where the water temperature is 6 degrees Celsius. The water temperature at the surface of the lake is 18 degrees Celsius. At the bottom of the lake, the pressure due to the depth of water is 1.56 times 10 to the 5 pascals. As the bubble rises through the water, the diameter of the bubble increases as shown. Okay, calculate the diameter d of the bubble just before it reaches the surface of the lake, and we are given the atmospheric pressure as well as 1.02 times 10 to the 5. Actually, yeah, I'm going to explain as I go where we use that. So they don't give you enough space, by the way, for this problem. You need way more calculus to solve it. So anyway, for the bubble in the bottom, we have the relationship that pressure at the bottom times V, let me call it B. So B means bottom, okay, is going to be equal to the number of particles, in this case methane gas molecules, the number of particles in the bubble times K times the temperature of the bubble in the bottom is going, I mean, just writing down the ideal gas formula for the bubble when it's down there, and then P at the surface times V at the surface is going to be equal to N. It's still the same number of molecules times K times the temperature at the surface. If we divide these two, we get rid of N and K, and we don't know N anyway. Okay, so we find PB times VB over PS times Vs is equal to TB over Ts. Okay, we need to find the volume at the surface and later the diameter. Okay, so the volume of the bubble at the surface is going to be equal to the pressure at the bottom times V at the bottom over P at the surface times T at the surface over T at the bottom. Okay, And I'm gonna move on to a clean page. Okay, and let's write down this monstrous calculation. Okay, what is the pressure of the bubble at the bottom? So P at the bottom is what they give us, okay, 1.56 times 10 to the, oops, 1.56 times 10 to the 5 plus the atmospheric pressure, right? Because this whole thing is underwater, okay? And above the water, we have the atmospheric pressure, which is 102 times 10 to the 5, okay? So let's write that down. 1.56 times 10 to the 5 plus 102 times 10 to the 5, okay? Now the volume at the bottom is going to be 4/3 pi and then the diameter to the cube. 1.5 over 2 is 0.75 times 10 to the negative 3 to the cube, and that's the volume. And then we still need to multiply, I'm gonna use some extra space, with the temperature, okay? So this is still the numerator, guys, don't get confused, okay? So 273 plus 18 is the temperature at the surface, okay? Now, in the denominator, we need the pressure of the bubble at the surface, which is just the atmospheric pressure, so 102 times 10 to the 5, okay? And okay, this is right below the surface, but still the atmospheric pressure. And then in the denominator, we need to multiply by the temperature. Wait, I think I messed up something. Let me think. What did I mess up? Yeah, the water temperature at the bottom. Oh yeah, it's at the surface. Okay, and then we need the temperature at the bottom, which is 273 plus 6, right? Yes, plus 6. Okay, so maybe we do, let me remove that fraction over there, and we can write it as like this. So this whole thing in the square brackets is multiplied by that number, okay? So I hope this makes sense. So the final result is 4.66 times 10 to the negative 9 cubic meters. Okay, so now this is the volume, right? So, but the volume is 4/3 pi times the radius cubed at the surface, okay? So this is going to be equal to 4.66 times 10 to the negative 9. Therefore, RS is going to be, so RS is 104 times 10 to the negative 3 meters. Therefore, the diameter at the surface is 2.08 times 10 to the negative 3 meters, okay? It's not a very hard problem conceptually, but it's easy to mess up the calculations, I think. Okay, let me know what you think though. So this was question 14, right? There is no second part. Yes, so let's move on to question 15 now. Okay, question 15. Sirius is the brightest star in the night sky. Canopus is the second brightest star. Show that the luminosity of Sirius is about 9.7 times 10 to the 27 watts. And they give you the radius of Sirius and the surface temperature of Sirius. So we just need to use the Stefan Boltzmann law. So L is sigma times the surface area times T to the 4. So we have 5.67 times 10 to the negative 8. And the units are watts over meters squared, and then Kelvin to the 4th, okay. Surface area is 4 pi times 1.18 times 10 to the 9 to the 4th, Kelvin to the 4th. Oops, what am I doing? Sorry, guys. Okay, this also needs to go. So this is 4 pi r squared. So this is the radius squared. I'm sorry. So we have meter squared. Okay, small mistake. And then surface temperature is 9,940 to the fourth. So kelvins to the fourth. So kelvins go. And we are left with 9.69 times 10 to the 27 watts as the answer. Okay. A teacher claims that from Earth, Sirius appears twice as bright as Canopus. Assess the accuracy of this claim. They give us the luminosity of Canopus, the distance of Sirius from Earth, and Canopus from Earth. So we need to compare the intensity of radiation that we receive from both stars, pretty much. So the intensity of radiation from Sirius is equal to the luminosity of Sirius over 4 pi ds squared. Okay, so we will use what we just calculated. Okay, over 4 pi 8.15 times 10 to the 16 squared. This is watts per meter squared. So the final result is 1.16 times 10 to the negative 7 watts per meter squared. And then for Canopus, we have L of Canopus over 4 pi dc squared. Dc is not the comics, it's the distance from Canopus. So 4.12 times 10 to the 30 over 4 pi, and then 2.93 times 10 to the 18 squared, which is the distance. This is watts per meter squared. So the final result is 3.82 times 10 to the negative 8 watts per meter squared. Okay, and if we divide these two, so IS over IC, we get 3.04, which is larger than 2. So teacher is wrong, just like the student from the earlier question. Okay, this was question 15. Let's move on to question 16. I have to say that I found this test one of the easy ones, I want to say, but I don't want to discourage anyone. Maybe some of the things here are hard and I don't see them, I don't feel them as hard. But compared to other tests, I think this one was okay. But let me know what you think in the comments. So 16 is actually a long writing problem. It should have an asterisk, I believe. I don't know why it doesn't have an asterisk. But anyway, so the diagram shows some equipment that could be used to calibrate a thermistor. Okay. Describe a method a student could use to obtain a calibration curve for the thermistor from 0 to 100 degrees Celsius. You should identify any extra equipment that would be needed. So let's write again with this kind of questions where you just have to write sentences down. If it's a 6-mark question, it means that you have to provide about between 5 and 7 sentences. So usually 6 is the optimal, of course. If it's a 4-mark question, you have to write down about 4 sentences, but it's not always, this is a general rule. Sometimes 2 sentences might be enough, but I'm just giving you some general exam tips. So add ice to water to bring it down to 0 degrees Celsius as the starting point. Okay, second point, use a thermometer placed close to the thermistor, okay, to measure the water temperature accurately. Okay, record the resistance shown on the ohmmeter, okay, for each measured temperature. Okay, heat, the other point is, okay, let me use a clean page. So heat the water using a Bunsen burner. So heat the water using a Bunsen, I think, burner or electrical heater. Okay, stir the water regularly, to ensure uniform temperature throughout. And finally, once you have all these measurements, you can plot a graph, of resistance against temperature to obtain the calibration curve. Okay, this was question 16. I hope it covers the question and that what I'm writing here is understandable. I receive some really mean comments sometimes about my handwriting, and I just saw a message saying that my accent is weird, which is, I don't know, it didn't feel nice. So anyway, I'm doing my best here, guys. So maybe I'm not doing my best. I don't know. Maybe I can do better. But okay, I mean, I never thought that I would have a YouTube channel discussing A-level physics. It's not very new. I mean, it's been 2 years on the making now, almost, this channel, and it started taking off. It makes me happy, but sometimes, it's gets into your head when you make a video and it doesn't land at all, or it's people are not happy with it, etc. So anyway, but anyway, I'm trying to say that if something I talk about doesn't make sense, just ask me in the comment section and I always reply. So anyway, let's move on to question 17. Okay, question 17. Arcturus is a red giant star. By the way, Arcturus in Greek means the bear. Okay, it's actually in ancient Greek. I mean, if you use it in modern Greek, they will understand what you're trying to say, but it's not used anymore. There is a modern word which is arcuda, which is kind of very close, but it's different. So anyway, when the spectrum of radiation received from Arcturus is analyzed, the spectrum is found to be shifted compared with the radiation received from the Sun. Part of the spectra of radiation from Arcturus and the Sun is shown. So we have the relative intensity and the lambda in the bottom. Explain why the spectrum of radiation received from Arcturus is shifted as shown. So we see that if you take Sun as the wavelength in the lab, the reference lambda, okay, we see that the radiation received from Arcturus is shifted towards larger lambda because on the Sun, what is that? 883.85 nanometers is the lambda for the Sun, and for Arcturus it's 884 nanometers, so it's redshifted. Okay, so that means that Arcturus is moving away from us. Okay, so that's the answer. So Arcturus is moving. Actually, let me move to the top line so I have space. Okay, Arcturus is moving away from the observer. Okay, away from the observer. We can write receding. So Arcturus is receding, is the more scientific term. So this causes a Doppler shift. Okay, stretching. Stretching the received wavelengths to larger values. So redshifted. So redshift. Okay. So yes, I think that's enough. Let's move on to part 2. Determine the speed of Arcturus relative to the Sun. So we need to find z, the Doppler factor, which is equal to delta lambda over lambda of the Sun, which is the reference in this case. Okay, so we can read it from the graph. So in the mark scheme, they found delta lambda to be 0.15 nanometers. I think this distance, okay, actually let me write it again. So I think this is delta lambda. Okay, so delta lambda is about 0.2 nanometers, but you can judge for yourselves. They give you a range of values as correct ones, okay? And lambda of the sun is about 883.85 is what I found, nanometers, okay? So let's write those down. 0.2 over 883.85, which is 2.26 times 10 to the negative 4. It's a unitless, dimensionless number because we are dividing nanometers with nanometers, right? So we get a pure number, okay? And that pure number, z, is equal to the velocity of the galaxy, of the star, over c. So v is z times c. So 2.26 times 10 to the negative 4 times 3 times 10 to the 8, which yields 6.8 times 10 to the 4 meters per second. Okay, this was part 2. Okay, part B, when light from galaxies is analyzed, a shift towards greater wavelengths in the in the spectra of radiation is observed. Describe how astronomers use a knowledge of these shifts to determine the distances to distant galaxies. So the first step is to measure the redshift, so z, which is equal to delta lambda over lambda. So measure the redshift of spectral lines, okay, from the galaxy, okay, from the galaxy you want to calculate things for. Use the Doppler relationship to calculate V, okay, and I remind you that Z is also equal to V over C, okay, and then apply Hubble's law, which I remind you is V is H naught times D. H naught is the Hubble constant and V is the speed you just calculated, so you can find D this way, okay? So apply Hubble's law to find D, the distance, okay? There's nothing more to add. Let's move on to the next question. 18. In the 17th century, Galileo observed the planet Jupiter through a telescope and discovered a number of moons orbiting this planet. Question A, Galileo made observations of the movement of these moons for 8 days. The largest moon is Ganymede. Deduce whether 8 days would have been enough time for Galileo, to be sure that Ganymede was orbiting Jupiter. Okay, so the force of gravity provides the centripetal force for Ganymede. So, if you have Jupiter and then that's Ganymede, then the force from Jupiter is the centripetal force, okay? So F gravity is m of Ganymede times omega squared times the radius, okay? This force is G times the mass of Jupiter times the mass of Ganymede, which I denote with lowercase m over r squared, and this is equal to m, and then omega can be written as 2 pi over the period, and then if we square it, we have 4 pi squared over t squared times r. Okay, so mass cancels. So we can write this as t squared is 4 pi squared times r cubed over g times m. Okay, which is Kepler's second law, I think this is how it's called. I forgot now. I think I mentioned it in one of my videos where I explain these things in the form of a lesson. So anyway, let's plug in numbers. 4 pi squared, the radius cubed, 1.07 times 10 to the 9 cubed. Okay, so we have meters cubed, and then over G 6.67 times 10 to the minus 11, and then in the denominator we have newtons over kilograms squared times meters squared. Okay, and then the mass of Jupiter 1.9 times 10 to the 27, that's in kilograms, so kilograms cancel. So, okay, so this is what is left. Okay, and this evaluates to 3.82 times 10 to the 11 kilograms times meters over newtons, but the newton is a kilogram times meters over seconds squared. Okay, and now we have to take the square root of this expression. So T is 6.18 times 10 to the 5 seconds. And if we divide, actually, let's do it somewhere else. So 6.18 times 10 to the 5 seconds over 8.64 times 10 to the 4 seconds, which are the seconds in a day. Okay, we find 7.15 days, which is less than 8 days. So enough days have passed, something like that. Actually, let me write it better because I'm being sloppy. So okay, the orbital period is 7.15 days, and Galileo was observing for 8 days, so that was enough to observe full revolution. So Galileo had enough time. Okay, so that is the answer. It's crazy to think about it's crazy to think about, but Galileo, I don't know why I'm messing this up, figured these things out 400 years ago. Without ChatGPT, no Claude, no AI, no calculators, no computers, not even telescopes. He invented the telescope to observe these things. So crazy. So let's move on. B. Show that the gravitational field strength at the surface of Ganymede is about 1.4 newtons per kilogram. So G is gm over r squared. They give us the radius and the mass. So 6.67 times 10 to the negative 11 newtons meter squared over kilograms squared times 1.48 times 10 to the 23 kilograms over r squared. 2006 what am I doing? So 2,640,000 meters actually squared. Okay, because they give us the radius in kilometers. So if you do this, you find 1.42. If you perform the calculation, I mean, you find 1.42 newtons per kilogram. Okay, part 2. The radius of Ganymede is about 50% larger than the radius of the Earth's moon. Explain what can be deduced about the mass of the Earth's moon from this information. The gravitational field strength at the surface of the Earth's moon is similar to the gravitational field strength at the surface of Ganymede. Okay, so they tell us that the radius of Ganymede is equal to the radius of the moon plus 50%, so plus 0.5 r of the moon. Okay, and they also tell us that the g of the moon is about the same as the g of Ganymede. So let's take this equation and expand it out. So g times m of moon over r of moon squared is going to be equal to g times mass of Ganymede. So that's a g, I'm sorry. Mass of Ganymede over 1.5 squared the radius of the moon squared, so that cancels. So we can find that the mass of the moon is 0.44 times the mass of Ganymede. And if we use the mass of Ganymede, we find that the mass of the moon is 6.58 times 10 to the 22 kilograms, which is kind of close to the real value, which is 7.35 times 10 to the 22 kilograms. Okay, so it's not very accurate, but close. All right, let's move on to the next question. 19. The photograph shows a spring balance. A scientist calibrated the spring balance. She added known masses to the balance and determined the extension of the spring. A mass of 550 grams was added to the balance and the spring extended by 11.9 centimeters. Show that the stiffness of the spring is about 45 newtons per meter. So this is simple. M times G should be equal to K times delta X. So K is mass times G over delta X. So we have 0.55 times 9.81 over delta X, which is 0.119, and that's newtons per meter, which is equal to 45.34 newtons per meter, which is about 45 newtons per meters as stated. Part 2. The spring balance can be used to determine the mass of a small animal without causing harm to the animal. The animal is placed in a bag. The bag is hung from the spring balance as shown. Imagine how crazy this would feel for the animal. Some weirdo animal with two hands grabs you, puts you in a bag, and then on a spring balance. It should feel crazy. So anyway, the spring extended by 5.8 centimeters when the bag with the animal was hung from the spring balance. When the mass of the animal was being determined, the bag started to oscillate with simple harmonic motion. Calculate the frequency of oscillation of the bag. Okay, let's find the mass first. So M times G is K times delta X. So let's find the mass of this animal. So mass is K times delta X over G. So 45.34, which is K, times delta X, which is 0.058 over 9.81, yields 0.268 kilograms. The period is then 2 pi times the square root of M over K. So 2 pi times the square root of 0.268 over 45.34. So 0.485 seconds. So the frequency is 1 over t, so 2.07 hertz. Okay, let's do part B of question 19. When the mass of one animal was being determined, the amplitude of oscillation of the bag was observed to increase to a large value. Explain this observation. So we're going to imagine that the animal is moving in such a way that it creates a resonance, okay? So the animal was moving because imagine how scared it will be, okay? So the animal was moving at a frequency matching the natural frequency of the spring. And I ran out of space. We need to also write that resonance occurred, okay, which means energy is transferred to the system most efficiently, okay, causing the amplitude to grow large. Okay, so this was question 19. Let's move on to question 20. Main sequence stars, such as the Sun, fuse hydrogen into helium. The Sun emits radiation with a peak intensity at a frequency of 6.1 times 10 to the 14 Hertz. Show that the surface temperature of the Sun is about 6,000 kelvins. So we're going to use Wien's law. Lambda T is 2.898 times 10 to the negative 3 meters times kelvins. And C is lambda times F. If we combine these two, we find that T is 2.898 times 10 to the negative 3 over C times the frequency. And if we plug in the numbers, we find 2.898. We will need an extra space. I'm sorry. So let's use a clean page. So T is 2.898 times 10 to the negative 3 meters times kelvins, and then 6.1 times 10 to the 14. We have to divide by seconds, and then we have to divide this whole thing with the speed of light, 3 times 10 to the 8 meters per second. So seconds cancel, meters cancel, and we find 5,892.6 kelvins, which is about 6,000 kelvins. Okay. Part 2. The Hertzsprung-Russell diagram below is incomplete. Remember, we mentioned it earlier. Label the position of the Sun on the diagram with a cross and an S. So, okay, the luminosity of the Sun is 1. Okay. So something like that. And that's 6,000 Kelvin. We imagine it to be 6,000 Kelvin. So okay, this is the point. So this is the cross, and this is the Sun. Part 3. Add to the diagram to indicate the areas where the following stars are located. A, main sequence stars. So let's use red. So it's this diagonal that includes the Sun. So that's A. Red giant stars. Let's use purple. They are up here. Low temperature, very high luminosity. Let's call this B. And then white dwarf stars, they are in the bottom left. Very high temperatures, very low luminosity. So that's the white dwarf region. Okay, let's move on. Part B is another long writing problem. So 2 of them in the same paper. So maybe this paper was not as easy as I thought. So explain the conditions that were required to bring about and maintain fusion in the core of the Sun. Okay, let's start by stating that we need a very high T in the core. Okay. This gives protons sufficient kinetic energy to overcome the electrostatic repulsion between them. Okay, the nuclei must get close enough, okay, for the strong nuclear force to take over and fusion to occur. And remember that the nuclear force is attractive. It's stronger than the electromagnetic force, but it only acts in very small, very small distances. So they have to come really close together. Okay, so that's another thing we need to mention. We need a very high temperature. We mentioned the temperature. So we also need a very high density and pressure, okay, is also required. Okay, high density ensures a high collision rate for nuclei, a high collision rate between nuclei, excuse me. Okay, a high collision rate, okay, maintains the temperature and keeps the fusion process going. Okay, let's move on to question 21. So in 2023, scientists made a previously unknown, let me read it again. In 2023, scientists made a previously unknown isotope of uranium. In the sense that they created it. Okay, sorry, I was confused. This isotope, uranium-241, is very unstable and decays to an isotope of neptunium via Vita minus decay. I think I've heard about this somewhere, but I'm not sure. You can look it up. So, complete the nuclear equation for the decay of uranium-241. So, let's start with the Vita particle. It has 0 mass number and a -1 atomic number. Therefore, neptunium has 93 protons. So, 93 minus 1 is 92. And then we need 241 for the mass number because we need to balance the equation in both sides. Okay, part 2. The mass of a nucleus of uranium-241 is 241.06033 atomic mass units. Show that the binding energy of a nucleus of uranium-241 is about 3 times 10 to the negative 10 joules, and they give you the mass of the neutron. So the binding energy is defined as Z times the mass of the proton plus the number of neutrons times the mass of the neutron minus the mass of uranium-241 times C squared. Okay, so Z is 92, mass of proton is 1.67 times 10 to the negative 27 plus 149 times 1.68, excuse me, 1.68 times 10 to the negative 27 minus 241.06033 times 1.66 times 10 to the negative 27. And then we have to multiply by 3 times 10 to the 8 squared, and then the units are kilograms meter squared over second squared. And this monster of a calculation yields 3.42 times 10 to the negative 10 joules. Okay, which is close to 3 times 10 to the negative 10 joules as required. Part 3. Calculate the binding energy per nucleon of uranium-241 in MeVs. So B over A is going to be 3.42 times 10 to the negative 10 joules over 241, which is the mass number, and then we have to divide by 1.6 times 10 to the negative 19 joules per electron volts. So joules gets cancelled, and if you calculate this, you find 8.87 times 10 to the 6 electron volts, which is 8.87 MeVs. Okay, nice and simple. Let's move on to the next question. Okay, part B. The half-life of uranium-241 is 40 minutes. The half-life of uranium-242 is 17 minutes. Initially, a sample has the same number of uranium-241 atoms as uranium-242 atoms. The sample is left for a time of 30 minutes. Deduce whether the number of uranium-241 atoms will now be twice the number of uranium-242 atoms. So the nuclear equations are, for the decay, the number of uranium-241 nucleons left is equal to nuclei, is equal to n naught e to the minus ln of 2 times time over t1 half for 241. I hope this is not very confusing because that's supposed to be a subscript, okay? And then n of 242 is n naught e to the minus ln of 2 times t over t1 half for for neptunium 242. We can divide this to get rid of n naught, which is unknown, okay? And we find n241 over n242 is equal to e to the ln of 2, okay, times 30 minutes, right, times 1 over the half-life of T1, of neptunium 242, okay, so 1 over 17 minus 1 over 4. And this becomes positive because when we divide, so we have, if we have e to the minus lambda t, let me try to demonstrate. So what I did is that if we divide e to the minus x1 with e to the minus x2, we get e to the x2 minus x1. Okay, so this is what I did. All right. So if we do this calculation, if we evaluate ln of 2 times 30 times 1 over 17 minus 1 over 40, we find 0.703, which is equal to 2.02, which means that the number of uranium-241 atoms remaining is 2.02 times the number of neptunium-242 nuclei remaining. So, excuse me. So the hypothesis is correct. Okay, so this was Unit 5 from October 2024. If it feels a little bit rushed, it's because I want to put out some last-minute material for you guys. And then during the summer, I plan to start creating new type of content as well. And okay, of course, I'm gonna continue probably with these past papers because people ask for them. I hope these videos are useful. The general consensus is that they are useful. I received some really nice comments, but okay, occasionally people complain about my accent, about my handwriting. I do my best, but I'm a little bit older, so it's kind of hard to learn new tricks, but I'm doing my best. So anyway, let me know what you think about these videos in the comments. If you have questions, ask me in the comments, and I always try to help. And see you guys in the next video. Bye.